So my question for you guys is, if you could have any programming language L, where L is a set of strings. So you make a program L, and it's one string, and that string is a valid program. And if it's not a valid program, then it's not in the language. So that's how programming languages typically are defined. They're just one big set of strings, and it's an infinite set usually, because usually you can expand the expressions as big as you want or make the program as big as you want. Now that might be limited by like a linker. Maybe in C you're limited by how many, you might be able to only have like 1024 depth of expressions or something like that. But you might not have a limit on how many files you have. So there's that. Now, let's say you wanted to edit a very complex, large program. Well, as you're editing it, you realize that you have to go back every time you want to change it and edit this string. And so now you're kind of limited compared to what you really could do, because you see, if you always have to go back and edit a string and then assume that the string has to be correct for you to compile it and then you can run it, well, then you're kind of preventing yourself from finding kind of an in-between state where you take one program that you kind of know is already what you want or similar to what you want, but it might not be correct, or it might be correct but it's not. It might be a valid program, but it's not what you want logically in a program. So instead of finding the best, the fastest way to take the string and then come up with some algorithm to produce another string, which you have to verify as part of the program, why not just have the grammar of the program, the language itself, be what you use to edit the program and to run the program, or to compile the program, whatever, and inference it. Let's say it's like a scripting language. Well, now you can just take that definition of the program, and you can forget about trying to find a valid string or not. You can just use that definition and just kind of edit your own expression, if you will, or program from it. That's in memory, that's in RAM, that's just an object construction. It's not necessarily a string though. There might be a string that represents it, but you don't have to go through and spend the time parsing and unparsing. You can just bypass that altogether and just say, well, here's one program that I have, here's the abstract syntax tree, and instead of looking at the tree in a very complicated way where you show all the details, because obviously that's going to be hard to read for a human, but why not have a program that helps you look at the tree in such a way that it's more efficient for you to work with that tree than it is for you to work with the text. See, because we're used to this 80s method of always parsing and unparsing and then converting it and saying, well, the syntax tree is, more complicated to look at. Well, is it? Maybe you're just doing it wrong when you try to display a syntax tree. Maybe you're just showing too much information. You're just revealing it the wrong way. Because sure, like I could come up with a really simple small expression. Whoa! I could come up with a small expression and it would look simpler. By the way, I'm kind of doing some rock climbing. I'm taking a shortcut through a big I gotta climb that somehow to get to the other side. But maybe you're just, when you're displaying your syntax tree, you're just doing it wrong. And by wrong, I just mean you're not realizing that there's a way to simplify things down. So you don't have to display every single detail. If you have the sum of 5 and 2, and then you have the sum of that and 7, and then the product of the result of that and 3, sure, that will look really complicated if you draw a whole tree rather than just write it out as an expression. But which one will look more complicated at a higher level? When you got 1,000 expressions inside of each other, and you got a program that usually would take up 1,000 files. Well, now you don't want to look at all the expressions. You don't want to look at a string level. So then somebody comes up with a system and says, well, let's use files, and let's reduce it that way and have functions that are only 4 lines long. The problem with that is now you have to organize all your files. And you realize that the logic system that you're using to organize all your files is the same logic system as your programming language is in. And but then you have to hard code that, and then it has issues, and it's not even formalized, and it doesn't even have rules to it. So you now have like this definition of C, which is already corrupted, and then you have this C compiler, which is corrupted because it doesn't match the definition, and then you have the linker, which doesn't even have a definition, and then you have and then that has its own bugs and issues. And what if you want to go further than that? What if you want to organize it by the types instead of by files? Well, that's what I'm going to do. That's what I've been trying to do. That's what I've been wanting to do. See, I work for a company, and the professor who started the company realized, he said, hey, if you have programming language L, it's stupid to just bypass the formal semantics of it. We need to make the formal semantics of it. And then we can just generate a compiler and know that it's pretty much correct. And we can generate an inferencer. We can generate... And I said, wait a minute. That's a good idea, but can't you also generate like a refactoring tool? Like something to actually help you edit your code in the first place? See, because the way I see it, after I study Agda and Haskell, the whole point of type theory is to reduce complexity for the programmer. And I think I found a logic system. I think I found an answer by a professor from France. His name is Coquand. He made a proof software called Coq, C-O-Q. It's got a rooster as its symbol. And, well, there's a rabbit over there. It's got a rooster as its symbol. Well, what if we take his proof system and use it to scale so that we don't have to be stuck, with just like, the compilation time and then runtime, and then you're just kind of stuck in this these 2 levels. Because then what happens when you infer on yourself and you want to use eval? Everyone says eval is evil, don't use it. Because but they don't tell you exactly why. And the reason why is because you lose your mathematical properties. Like when you're using Lisp or you're using Haskell or something, you tell it, eval this other Lisp program or this other Haskell program indirectly. Well, you're not really doing it using the type system. What you're doing is you're using a file, and you're saying at this weird and kind of messy meta level, saying, I don't know the mathematical properties of this when I compiled you, but here's just a file. Here's a text file, and you can run this compile algorithm which matches it to the same logic which you're running off. Well, why would you do that? That doesn't make any sense. Why? You don't need to do that. The whole point is, it's like, I've had an argument with people about having nulls. Nulls are a mistake. Java shouldn't have them at that level. It doesn't make any sense. It doesn't. Because you can have optionals. The whole point of types is to prove your expressions. And so in this case, the whole point of the whole point of your type theory, the whole point is prove your expressions. When you reflect, you kind of lose that, and it's like weird because why would you want to do that? Now you don't have one system. Now you have a system within systems, and you have to manually do stuff now. The whole point of it is automation. You're supposed to be able to do it automatically. So and Coquin figured this out in a way, but he's a mathematician. He's not really a software oriented guru, you know, computer science oriented person. I think he's more oriented towards mathematics than that. And so he's using it for proofs. But Curry-Howard isomorphism, proofs and programs are the same thing from the point of view of types. I don't know if I heard like a rattlesnake or something. I don't want to mess with them at all. And where I'm at right now is kind of a weird spot. But you have to understand what I'm saying. Hopefully there's no scorpions here either. What I'm going to do is I'm going to take advantage of all the pure functionality that Haskell has. I'm going to take advantage, I'm going to use the same, Haskell uses I/O monads to do his input and output. Okay? Coq is for a proof system. I'm going to use the same logic system. Okay? I'm going to use hashing at a meta level on the software that basically runs the there's going to be a reduction algorithm which basically kind of replaces the interpreter, compiler, the editor. It kind of replaces all that. But the thing that runs it on the back end, the code that actually runs that is going to use databases and hashing to help it run efficiently. And I need help. I mean, I'm just one man, and I don't want to be defeated. I don't want to be defeated by this project and be like, this is too hard. I got to give up. People don't believe in it. You know, I went on Stack Overflow, and I did exactly what my boss told me to do. He said, go find famous, important C programs that if you find a bug in them, you'd be famous, you'd be lucky. That's what he said. He wasn't just trying to get, like, he was trying to get some popularity for their software, but they've been working on it for 15 years. There's nothing wrong with that. It's exactly what we were supposed to do. And people jumped on it, and they said I was asking a question that doesn't fit on Stack Overflow and all this stuff, and then someone commented, you're just trying to get famous. I did exactly what my boss told me to do. So, you know, I don't care. You know, I was doing the right thing, so don't. Wish me luck.